Hello and welcome to the third video in our Essential Skills series. You'll remember that we are focusing on those skills essential for physical science, and in this series, paper 1, the physics paper. I'm Dr. Derek Fish, Director of Unizulu Science Centre at the University of Zululand. In this third video, we'll focus on motion graphs. If you haven't watched video 1.2, which is the introduction to graphs, I encourage you to do that before watching this one, as that gives all the mathematical basis for the graphs we will now use. This is on pages 8 to 16 in your work booklet, so please follow as you watch this video. Before we go to page 8, let's just do a recap of the introduction and see where motion graphs fits in. So on page 3 in your booklets, we have the contents page. You remember we're looking at 4 essential skills: graphs, free body diagrams, equations, and multiple choice and ratio questions. Having done the introduction and the mathematical side of graphs, we're now going to focus on motion graphs as one of 4 examples of graphs. These particularly come up in question 3, the projectile motion question. On page 4, obviously, we are focusing on the mechanics section of your curriculum, and graphs come up especially in grade 10 and grade 12. You'll see in grade 10, it says description of motion in words, diagrams, graphs, and equations. And there's a prescribed experiment of velocity time graphs and acceleration, and a recommended experiment of position time graphs. Even if you didn't manage to do those, don't worry, we're going to do them today. Grade 11 is more about Newton's laws, and especially his second law and forces. But grade 12, there's a lot about vertical projectile motion in words, diagrams, equations, and graphs. And again, a recommended experiment of position time and velocity time graphs for free fall. On page 5, again, a reminder from the examiner himself that grade 10 and 11 work is poorly understood and needs to be identified with the work done in grade 12. So even if you are sleeping in grade 10 and 11, particularly Newton's laws and his universal gravitation law are important for this section. So just to remind you, if you've forgotten, Newton's first law, that everybody remains in a state of rest or uniform motion unless acted on by a net external force. It talks about constant velocity. Newton's second law, talking about acceleration, force equals mass times acceleration. The acceleration is directly proportional to the force and inversely proportional to the mass. And Newton's third law, the law of action-reaction, very important. Don't forget as well Newton's law of universal gravitation, G m1 m2 over r squared, particularly for attraction between planets, the moon and the earth, and so on. Remember, the fact that page 5 is in red here is to tell you we're still busy with page 5, but what you see on the screen here, you will not see in your books. Also on page 5, although it's not in your books, we looked at the weighting of different sections. Graphs of motion obviously falls under mechanics. It's 42% of the paper. It's the biggest section. And after the multiple choice, there are 4 of the long questions which deal with mechanics. Averaging the marks per question for the last 3 papers. Question 1, multiple choice, is always 20 marks. And then the 4 long questions on mechanics usually total 56 marks out of 150, more than a third of your paper. Let's take a look at the 4 mechanics questions, usually in the matric exam, and where motion graphs fit in. Questions 2 is usually on Newton's laws, especially his second law. Question 3 is vertical projectile motion, and this is the one we'll focus on in this video because this is where the graphs of motion come in. You will see that in November 2020 they gave you a graph and asked questions about it. November 2019 a sketch graph, again questions were asked, and November 2018 they asked you to draw a graph. Then the next one is a momentum question, and finally the work, energy and power question. So these are the 4 mechanics questions, but as we said, we'll be focusing on question 3 on vertical projectile motion. Further down on page 5, we looked at the skills from the CAPS curriculum guide, which are necessary for physical science. And for this particular section, particularly 2 to 5, understanding scientific notation, knowing how to convert units, changing the subject of a formula, and basic trigonometry skills. Those mathematical skills are very important here. Secondly, what is rate? All of the graphs in this section are rate graphs. We have position time, velocity time, and acceleration time. Those are all rate graphs, direct and inverse proportion, especially for Newton's second law, acceleration directly proportional to force and inversely proportional to mass, and the constants in the equation. You need to know your data sheets well for this section. Then under practical investigation skills, especially the graph skills, general types of graphs and analysis, and identifying your variables, independent, dependent, and control variables. Moving on to page 6, we introduced graphs to you. We said that there are 3 things that graphs show. As I've just mentioned, we will be focusing on rate graphs. Graphs where something is graphed against time, and they show the rate of change of position or velocity or acceleration. Also, the point at the bottom that a graph is not a photograph will come up very strongly in this section. We'll deal with this later in this video. Then also on page 6, what graph skills will be expected of you in exams? Particularly the first 3 usually come up with motion graphs. Analyze and explain trends in a sketch graph. Read values, gradient and intercept in an accurate graph. Draw your own sketch graph. That's quite often a question here. And then possibly even plot an accurate graph on graph paper provided. We also introduced you to some various graphs you are familiar with from mathematics on page 6, and particularly these 3, constant, linear, and quadratic graphs, come up under your motion graphs. Your acceleration time graph is usually constant, your velocity time graph is linear, and your position time graph is very often quadratic as long as there is some acceleration. We pointed out the fact that in question 3.5, you can find on page 15 from last year's exam, you've got a position time graph, which has indeed got some parabolas there. Now, what makes me sad and frustrated is so often I see students who are very good at quadratics in maths. Y equals x squared, function of x equals x squared, they have no problem. But as soon as we come to science with exactly the same graphs, they're not able to handle them anymore. Now, I'm going to make sure today that you are not one of those students. You remember on page 7, we identified the important equation for a straight line graph, y equals mx plus c. That's what the graph looks like. And it's very important to distinguish between your variables, y, the dependent variable on the vertical axis, and x, the independent variable on the horizontal axis, and your 2 constants. M is the gradient, the slope of the graph, c is the y-intercept. Now, of course, instead of y and x, we're going to be putting in real variables. So, for example, in a velocity time graph, your dependent variable becomes final velocity, and your independent variable becomes time. Time must always be an independent variable. In this case, the slope of the graph is just the acceleration, and the constant, the y-intercept, is the initial velocity. Now, we played with a fantastic PHET simulation to learn all about graphing straight lines. We're now going to go to another simulation, which is called graphing quadratics. Teachers, you do have this in your teacher pack. So let's see what we can learn from that. So let's see what we can learn from this great simulation. So the general equation for a parabola or quadratic is y equals ax squared plus bx plus c. A is the coefficient of x squared. At the moment, a has a value of 1. Let's see what happens when we change the value of a. If we increase it, the curve gets tighter and steeper. If we decrease it, the curve gets wider until if we go down to 0, it can actually be a straight line. If we keep going down, a negative a actually gives us an upside down parabola. Now, this is a very important form because with projectile motion, with velocity being upwards and the force of gravity or the acceleration being downwards, you very often have a negative value of a. So we get graphs which are this shape. What does c do, the y-intercept? Well, once again, as for straight lines, it simply moves the graph upwards, and downwards. Without moving it to the left or the right, it changes that y-intercept. So let's go to a positive parabola again. And I wonder if you can work out in your head what will happen if we change the value of b, the coefficient of x. This is very difficult, but basically changing the value of b moves the parabola to the left and the right, as well as up and down. You can see it kind of moves it around in an arc. That's not too important really at this stage. Now we know what happens with the quadratic. Let's remind ourselves of a straight line graph. If we keep the value of a at 0, so we just have bx plus c. B, which we called m before, is just the gradient of the graph, positive gradient and negative gradient. And c, once again, as always, the constant is the y-intercept, which just has the effect of moving the graph up and down on the screen. So I hope that was helpful to you, and teachers, I really encourage you to use this simulation, graphing quadratics. There's so much that can be learnt which can really help with pupil understanding. So again, this is not on your page 7, but if we took the standard form for the quadratic, y equals ax squared plus bx, again, we have variables. Y is the dependent variable on the vertical axis, x is the independent variable on the horizontal axis. And our constants, a is the coefficient of x squared, b is the coefficient of x. We've just made c equal to 0 for the time being. Once again, with motion graphs, these will become real. So in place of y, we'll have position, x. In place of x, we'll have time. And this is a typical graph, position time, when there is accelerated motion. This is the equation from your data sheets. Delta x, or displacement, equals half a delta t squared plus vi delta t. So now our constants, it's a little bit confusing because a becomes half a, but it's half the acceleration. That's the coefficient of delta t squared. And the coefficient of delta t is vi, the initial velocity. Because of that t squared term, we have a parabola here rather than a straight line. Now, all this theory is going to make a whole lot more sense when we look at actual motion graphs, and more importantly, when we produce motion graphs in a real experiment. Now, once again, we're going to use the fantastic equipment supplied by Pasco Scientific, and I have here the Pasco motion sensor. Now, this motion sensor actually sends out a radar beam. So from that circular gold disc, it emits a radar, and that bounces off the target, which in this case is going to be just myself, and then it returns where it's detected. Now, by timing very exactly how long that radar beam takes to go out and come back, it can measure the distance that I am away from the sensor. So it is going to take a reading of position, and then of course the computer has a clock, and it's very easy for it to graph that position against time. Let's see how it works. So I'm standing in front of the motion sensor, and it's measuring that I'm 0.6 meters away. If I start walking slowly backwards, you can see that reading increases. And I'm now 1.5 meters away. Stand still again, and you see the line is flat. Move further back again, and again my position increases. And when I stand still, again the line is flat. Now I'm going to come back quickly to the start, and then we're going to stop. Right, so let's have a look at what happened there. You can see very clearly what my motion was by looking at the graph. At the beginning, I was standing still, so the graph is flat. When I started walking away, the graph was increasing, and the positive gradient shows a positive velocity. Again, the graph is flat, showing that I'm standing still, and again, walking away this time a little bit more quickly. Graph is flat at the top to show that I'm standing still. And then when I came back, the gradient is negative, showing that I'm moving back towards the start, and it's very steep, which shows that I was moving very, very quickly. I hope you enjoyed seeing how position time graphs are really made using the motion sensor. I always feel that science becomes much more real when we do experiments. Let's consolidate this knowledge on page 8 in your books. Let's turn to page 8. First of all, let's look at position time graphs. What do the different shapes of graph mean to us? So just going through this list on the right-hand side. First of all, the red line indicates an object that has stopped. It's stationary. And a horizontal straight line tells you that the position is not changing, so the object has stopped. If the line is sloping up, like either of these two blue lines, it tells you that the object is traveling at a constant speed because the gradient doesn't change away from the start. So the position is increasing. That's a slower speed, that's a faster speed. The green line here is a constant speed back towards the start, so it has a negative gradient. If the line is curved, it tells you that the speed is changing and there is acceleration taking place. If it is curved up, like this purple line, then the object is accelerating, it's getting faster, and the velocity is increasing. If it's curved down, like this orange line, the object is slowing down or decelerating. Even though the velocity is decreasing, please remember that this object is still traveling away from where it started. So the position is still increasing. Remember, if lines have equal gradients, they show equal speeds. Finally, when is the object at the starting point? Well, in this graph, there are two positions, at the beginning and at the end. So at the 0 point of position, that is when the object is at the starting point. Now, perhaps again, open your books wide so you can see page 8 and 9 side by side and compare these two graphs, because it's quite different for a velocity time graph. And you need to make sure you know which graph you're looking at. With a velocity time graph, a flat line does not mean it's standing still, but it means constant speed or zero acceleration. So for all this time, the object was continuing to move quite fast, but the velocity was not changing. If the velocity time graph is sloping up, like this blue line or this one, it tells you there's a constant acceleration, which is positive, and the speed is increasing. If it's slowing down, like for this green line, it's a constant deceleration or negative acceleration, and it is decreasing speed. Now, you could have a curved line on a velocity time graph, but that means a changing acceleration, and you're unlikely to encounter that while you're still at school. Once again, two lines with equal gradients show equal accelerations. And finally, when is the object stationary? When is it not moving? That's when it is on the x-axis. So at these 2 points, the object had actually stopped. It was not moving. Now, let's see how much I understand about motion graphs by giving myself a little test on another fantastic Pasco application called MatchGraph. Right, so here I am with Pasco MatchGraph. You will see there's already a black line drawn on the screen. I have to try to walk in such a way that my red line from my walking matches the black line as closely as possible, and it will give me a score. Let's see how I do. Let's go. I need to adjust my position. I have 3 seconds, and then I must walk. Oh, too fast. Let me come back a bit. Too far. Got to get onto that black line. We're getting closer. See if I can end in the right place. Okay, that wasn't too bad, 73%. But you can see that my red graph was actually quite far from the black graph. I'm sure I can do better. Let's try a second time. Let's go. I'll adjust my position. Now I'll move a little bit more slowly and try to keep my gradient right so that my red line stays right on top of the black line, right up till the end. That was great. So I think you can see that my second effort was much better than my first, 97.35%. You can see that the red line is very close to the black line. They're almost parallel. They have the same gradient, which means that my velocity was well matched. You can just see at the beginning, that line is curved because it took me a little while to attain the speed that was correct. When the red line is below the black line, means I was moving too slowly. When they were right on top of each other, I was going at just about the right speed. Let's try something a little bit more challenging. So here's a graph which actually has 5 separate parts in it. And I'd like you just to think a little bit what those different parts represent. And if you were in my place, and if you were trying to walk to match this graph, what should you be doing at each of those times? Perhaps the teacher would like to pause the video here and talk about what each part of the graph represents before we try it. Right, so let's go. Let's see how I do. Uh-oh, I'm too far away. I need to get much closer. That should be standing still. Let me catch up. That was a bit fast. Oh, let me try and get back to this. That was too fast. Let me get back onto that line. Sure, at least I ended well, but 79.34 is not too good. Let's see if I can do a little bit better a second time. Let's try again. I'm adjusting my position. Stand still, walk away quite fast. Stand still again, walk back slowly, not too fast, and stand still. That was great. So what you can see very nicely here is the difference between the black line, which is a theoretical line, and the red line, which is the experimental one. See, the black one has got very sharp turns. The red one has got rounded turns. In reality, it's impossible to make those sharp turns. You see, the curve there shows that it took me a while to accelerate up to speed. So where did I go wrong? Well, my speed was about right, but I started moving a little bit too late. Also, I went a little bit too far. I think my brakes were not working. And then when I came back here, the gradient of the line was a little bit too steep. So I went below the black line, but I ended in about the right place, about 10 centimeters short. So all in all, not a bad effort. I wish that all of you could have the chance to try an exercise like this. So let's end with something really difficult. Instead of having a position time graph, let's have a velocity time graph. I'd really like you to think about this for a while. And again, teachers, maybe pause the video. This graph is also in 5 pieces, and try to think about what do the different parts of this graph represent? What type of motion is represented by each part of the graph? I'm going to have a go at walking this one, but I want to tell you this is very difficult. See if you can make sense of it. So let's give this one a try, although this is very difficult, but I'll do my best. Let's go. Standing still, getting ready for the start. Right, stand still, walk away at constant velocity, stand still again, come back at slow forward velocity, and stand still. 92.72, actually I'm quite proud of that. That's great. So that PESCO match graph activity is a great way to learn more about graphs of motion. What you saw when I tried it was it's quite easy to understand the position time graphs, but the velocity time graphs are much more difficult to understand. And just looking at a graph like this, it takes quite a lot of thought to work out what's going on at each stage of the graph. Now, for matric, you need to be able to move between position, velocity, and acceleration time graphs. Now, I want to help you to do that. So let's turn immediately to page 10 and 11. And again, this is a double-page spread, so please don't fold your books over. Open them up wide so you can see both pages at the same time. Now, unfortunately, your books don't have color in, but you'll see that there are 4 columns. The first vertical column are position time graphs, which are blue on my screen. The next column are velocity time graphs, which are red on my screen. The next column, acceleration time graphs, which are green on my screen. And the 4th column tells you about the types of motion. If you look at the horizontal rows, the top row is motion at constant velocity with 0 acceleration. The middle row is motion with positive acceleration. In other words, a car speeding up. You're pressing the accelerator and going faster. The bottom row is motion with negative acceleration, sometimes called deceleration, when you're pressing the brakes and slowing down. Please notice in all 3 cases, the car is moving forwards, which is to the right in our diagram over here. So let's look at these one row at a time so we can understand them a bit better. Let's start with the top row in your pages 10 and 11, which is for 0 acceleration. So this is what usually happens when you're driving a car. You get onto the freeway, you reach a steady speed of 100 kilometers per hour, and you keep that speed. Newton's first law applies because there's no change in the forward velocity. So acceleration is 0. Now please understand that these 3 graphs belong together. In other words, when the acceleration time graph looks like that, the velocity graph will look like that, and the position time graph look like that. They all describe exactly the same motion, which is motion with zero acceleration. It's usually easiest to start with the acceleration time graph. At school, your acceleration time graphs will always be horizontal straight lines. So acceleration is constant and it is zero. Because of that, the velocity time graph is a constant. The initial velocity is the same as the final velocity and every other velocity. It doesn't change with time because acceleration is naught. Your position time graph increases linearly because your acceleration is naught. So it's a straight line graph. Please notice the gradient of this graph is just the velocity, that initial velocity. And if you look at the area under the velocity time graph, that gives you the displacement. So remember, to go from position to velocity, you take the gradient, velocity to position, you take the area. So in this case, we have a linear equation, delta x equals vi delta t, because the acceleration is equal to naught. So that's the simplest case, constant velocity motion. Looking at the middle row in your books, positive acceleration. So this is where we have Newton's second law. You have a force which is providing an acceleration which changes the velocity. So now your acceleration time graph, it's still a horizontal straight line, but it's above the axis, it's greater than naught. Your velocity time graph is no longer horizontal, it is increasing. From that initial velocity, it increases as time passes. How does it increase? Well, the gradient is just acceleration. So we have this linear equation. Final velocity equals initial velocity plus a times delta t. We remember that acceleration is greater than naught here. Your position time graph is increasing, but as a parabola. And it's that term delta t squared from your data sheets, which shows why it should be a parabola. Remembering again that acceleration is greater than naught. Looking at velocity and acceleration graphs, again, the gradient of velocity gives you the acceleration, and the area under the acceleration time graph would give you the velocity. Let's look at the last case. In the bottom row, we're looking at negative acceleration. So this graph is below the axis. Acceleration is still constant. It doesn't change with time, but it's less than naught. Maybe it's -2 or -3 meters per second squared. Your velocity now decreases. Starting from some initial velocity, it decreases with time. And so we have the same equation, but now we remember that the gradient, the acceleration, is less than naught, so you have a negative slope. Pupils often make the mistake of thinking if the velocity is decreasing, the position is also decreasing. It's not. Remember, when you put your brakes on in the car, you're still traveling forwards. But instead of the graph curving up, it curves down. So this is an upside down parabola. We flipped it upside down. Why? Because a is less than naught. So again, the same equation, but governed by the fact that acceleration is less than naught. Now, once again, it's very difficult just to see these in abstract. We wish we could actually see this car moving, but in a way we can with a wonderful simulation from PHET called the moving man, which allows us to see both the graphs and the motion which produces those graphs. As before, the moving man is in the teacher pack, and teachers, we encourage you to use this and to experiment with it. The moving man allows you to move a man around, and you can see position, velocity, and acceleration are measured. Or we can put him on one side here. Let's reset all the figures, and let's just say, right, let's give him an acceleration of about 1.2 meters per second. Put him right on the side here, and let's see what happens. So I'm going to give an acceleration of 1.2 meters per second, and we can play it back and see what happens. So what's really more useful here is to look at the charts. So you can see here, just like we had before, we've got a position time graph, which is going to be blue, velocity time graph, which is going to be red, and an acceleration time graph, which is going to be green. Now keep your books open, showing you page 10 and 11. The first simulation we're going to do is simply the top row. So we've got the man right on the left here. We've got a positive velocity of 2 meters per second and 0 acceleration. So we'll just allow it to go, and we'll observe. The position time graph is increasing as a straight line. velocity time graph is a horizontal straight line, and acceleration time graph is simply 0. Now, it's interesting, we can play this back, and it's interesting to have a look at the vectors. You can see the velocity vector there, and you can see the velocity vector doesn't change because there's no change to the velocity in all the time that he is moving here. So let's have a look at the middle row on your pages 10 and 11. Again, we've put the man right on the left here. We've given him an initial velocity of 1 meter per second and an acceleration, a positive acceleration of 0.1 meters per second squared. Let's see what happens. So again, you'll see the acceleration stays constant, but velocity is increasing as a straight line and position is increasing as a curve. Let me stop it there. If I expand the time scale a little bit, you can see what has happened here. So acceleration is constant. It's a very small acceleration, but I think you can see it's just above the axis. From an initial velocity of 1 meter per second, you can see that the velocity has increased, but it's increased as a straight line, whereas the position time graph is now curving upwards. Once again, it's interesting to look at the vectors. The acceleration vector, which is green, will not change, but just watch how the velocity vector increases, the red one, as he moves faster and faster across the screen. So you can see that red vector is slowly growing as his velocity gets larger. And now let's do the bottom row on page 10 and 11, negative acceleration. You can see we've given him an initial velocity, quite a large one, of 6 meters per second. You can see the arrow there. And we've given a negative acceleration of -1 meter per second. I'll just expand the scale so that is easier to see, and also for velocity. Now, I want you to notice those arrows carefully because the acceleration will not change, but the velocity will decrease. Let's have a look. Okay, and again, let me expand the time scale so we can see what has happened here. So I think it'll be interesting to play this back again. And you can see what happened there. So he started with a large initial velocity, but because the acceleration was negative, we have a negative gradient on that line, and it decreased right down to 0. And we can move him backwards and forwards. And you can see because the green arrow of acceleration was opposite to the red arrow of velocity, velocity decreases and decreases and decreases until we get right down to 0. So I think you'll agree that the moving man really helps us understand all those graphs which are on page 10 and 11. I want to tell you these 9 graphs here really represent all the different types of graphs you'll encounter at school level. When you get a more complicated graph, all you need to do is break it up into different sections. And you should be able to translate a velocity graph into the corresponding position graph and so on. Let's have a look at how that works on page 12. Now, if you look at the velocity graph on page 12, it looks terribly complicated. And you might think, how can I possibly understand this? Well, the way to do it is to break it up into small pieces. You know, someone was once asked, how do you eat an elephant? And the answer is 1 mouthful at a time. So here we need to divide it up. And you can see we've already divided the graph for you into 6 parts. So we've got position, velocity, and acceleration versus time graphs. We've matched the time axes so that section A on the position graph is the same as section A on the velocity graph, the same as section A on the acceleration graph. It's the first 4 seconds of the motion. We've got the graphs and a verbal description of the motion. Now, once again, let's look at position and velocity graphs. May I please remind you that this graph does not represent a car which drives uphill A, down into the dip, and up another hill. Please, there are no hills, there are no valleys. The car is going to the right, turning around and coming back to the left in a straight line. It is one-dimensional movement. So basically what we're seeing here is a car that starts from home. So there's 2 times the car is at home, at 0 seconds and at 24 seconds. But there's actually 3 times that the car has stopped. Can you work out at what times the car is stationary? of course at 0 and 24 when it's at home, but actually also at 12 seconds when it turns around, it's momentarily stationary. So looking at the description, the driver leaves home and presses the accelerator and speeds up away from home for 4 seconds. Then maybe he's reached the speed limit, so section B, he travels at a constant speed of 4 meters per second for 4 seconds, still moving away from home. Then he maybe sees a stop sign, he presses his brakes, and he slows down, but he's still moving forward. How do we know? Because the position graph is still increasing. He comes to rest. Then at the end of section C, he remembers he's forgotten his cell phone at home. So he instantly turns around and starts accelerating back towards his home, with his velocity becoming increasingly negative. Then reaching the speed limit, section E, he travels at constant velocity for 4 meters per second, still towards home. And then section F, he presses the brakes and slows down because he doesn't want to go through his garden gate, and he comes to rest outside his house. So velocity is positive for half the time and negative for half the time. It's changing during sections A, C, D, and F, and it's constant for B and E. The position time graph tells us that for A, B, and C, the car was traveling away from home, but for D, E, and F, it was traveling back towards home. Notice when the velocity is constant, position time graph is a straight line, B and E, and it's a parabola for the other sections, curved up for A and F, and curved down for C and D. Comparing the velocity and acceleration graphs, the acceleration graph always is just horizontal straight line. So we have positive acceleration, 0 for B, negative acceleration for C and D, 0 for E, and positive acceleration for F again. Now remembering that the acceleration is the gradient of the velocity time curve. When acceleration is positive, velocity slopes up. When acceleration is 0, velocity is flat. When acceleration is negative, velocity slopes down, even with a change of direction. When acceleration is 0, velocity is constant. And when acceleration is positive, velocity slopes up. Now, once again, this is going to be much easier to understand if we can just see it with the moving man. So we have set up the moving man, just like your graphs that are there on page 12. Unfortunately, we couldn't set up all the times and distances exactly the same, but it doesn't matter. The important thing is there are 6 distinct parts of this graph. And what's nice is you can watch the motion of the man at the top, like this. Perhaps I'll make my screen disappear for a moment so that it doesn't block him. Now, let me switch on the acceleration vector, which is the green vector. And you'll be able to see, let's go right back to the beginning. At the beginning, the acceleration vector is positive. That's A. For B, it is 0. For C, it is negative. For D, it is still negative. For E, it is 0. And for F, it is positive again. Let's try that again, and let's have a look at the velocity vector this time. So if we go right back to the start, we'll see at the beginning his velocity is 0. Then his velocity is increasing positive, constant positive, decreasing positive for C. Then he turns around for D, it's increasing negative. For E, it's constant negative. And for F, it is decreasing negative until he comes to rest again. Now, let's look at the two vectors together. So the green acceleration vector and the red velocity vector. And just watch how the direction of the acceleration vector causes the change in the velocity vector. And it's really nice to be able to see the motion as well as to see these vectors here. If we enlarge some of the graphs so you can see more clearly, you can see the position time graph clearly has a curve for A, straight line for B, curve for C and D, straight line for E, and a curve for F at the end as well. And you can see how these match up with the different velocity times. Again, just comparing all three graphs, let's look at a few of the important points. At the beginning, the position is 0, velocity is 0, it has an acceleration of 1. For section A of the graph, you can see acceleration is positive, velocity is increasing, and position is a curve. When we get to the second section of the graph, section B, you can see that now velocity is constant because acceleration is 0, but the man is still moving away. Section C, acceleration has become negative as he's applied the brakes, but he's still moving away. At the end of section C, we come to this point. Now you'll see that's the point, just you can see as I do that, that's the point where the man turns around. At that point, you can see velocity is 0, and you can see from the position time graph that he's turned around. Now, of course, the gradient at that point would be a horizontal straight line. It would also be 0. And from then on, he's moving back towards his home through section D, section E, and finally section F, and then he comes to rest. So once again, this great simulation has helped us understand our graphs of motion. Now, let's turn to page 13, because I can teach you as much as I want, but until you try it for yourself, you'll never know whether you can do it or not. So here's an exercise for you to do on page 13. There are 12 graphs which I want you to draw for 4 different types of motion, which are described there. Let me just explain them to you, and then you're going to pause the video and take 5 minutes or so to draw these graphs. So I'd like you to draw position, velocity, and acceleration time graphs for constant velocity motion. Let's imagine you're doing an experiment in the lab. You have a trolley, a dynamics trolley that rolls along a flat, frictionless runway. So you can have it starting from position 0, give it some initial positive velocity, and I'd like you to draw sketch graphs of position, velocity, and acceleration versus time. Secondly, you now tilt the runway so your trolley is rolling down the sloping runway. Again, just regard the top of the trolley as position 0, and your trolley is going to roll down a sloping runway, starting from rest, and I want you to draw those 3 graphs again. Getting a little bit more difficult. Number 3, a negative acceleration. Now with a sloping runway, you start from the bottom and you push the trolley uphill. You give it a hard push, so it starts with some positive initial velocity, and then that velocity is going to decrease. And I want you to describe how it moves, going up the runway, coming to rest, and then rolling back to the bottom again. So 2 movements. And then finally, the bouncing ball. This has come up in many exams and caused lots of problems, but we're going to sort it out today. So let's see how you do with that. Again, we have a sloping runway. You start the trolley at the top. So you can, I've done the position time graph for you. Start the trolley at the top. It rolls down to the bottom, and then because it has a spring, it bounces off the bottom, goes up till it runs out of speed, turns around, and comes back again. You can see that we've already put in that it loses some of its energy from that bounce at the bottom. So it doesn't come back up quite as high as it did before. So obviously there's an acceleration down the runway. I've already drawn that graph. I'd like you to draw the matching velocity and acceleration graphs. These are not so easy, and you'll need to think about them a bit. So teachers, please pause the video here for 5 minutes. It's very important that everybody tries these. Do them in pencil. Try to complete these 12 graphs, and then we'll come back and demonstrate and show you the answers. Well, I hope you had time to try these 12 graphs. So we're going to give you the correct answers, but rather just giving you the answers on screen, we're going to demonstrate the answers using this wonderful PHET simulation, the moving man. So for question 1 on page 13, the one that has constant velocity, you can see we've put the man on the left of our runway, given him an initial positive velocity of 2 meters per second, and acceleration is 0. And this is what the graphs look like. I hope your graphs look like this. Now we can do a quick playback here. And I think that this motion is very simple. The acceleration stays naught. The velocity is constant positive, and the position is increasing as a straight line. You can see the man keeps moving at constant velocity, and the red velocity vector doesn't change because there's no acceleration, there's no increase in velocity. For the second example, you can see we've set the initial velocity as 0, starting from rest, but the acceleration is 1 meter per second squared. Maybe you're expecting 10 for g, but just remember, unless you're falling vertically downwards, your acceleration will be some component of gravity, usually much less. Let's see what this motion looks like. And again, observe the vectors at the top here. So we can see very nicely here that the acceleration is constant positive. Let me enlarge the scale a bit. Velocity increases as a straight line, and position increases as a curve. Let's look closely at the position graph, and by expanding it, you can see very nicely it's definitely a parabola, definitely not a straight line, whereas the velocity, you can see, is a nice straight line starting from 0. Putting all the curves back, we can just do a quick replay to make sure that we've seen this. Again, please watch the vectors. At the beginning, the acceleration vector is 1 meter per second squared. That will not change, but I want you to watch the velocity vector grow as he moves from left to right and as he gets faster. So let's return to our PowerPoint and let's make sure you have the right answers recorded. Let's look at number 1 and 2. Starting with number 1, it's usually easiest to start with the acceleration graph. That is just naught, it's constant and 0. Therefore, the velocity graph starting from some initial velocity is constant, it's horizontal. Position graph increases as a straight line. Number 2, where there's a positive acceleration, the acceleration is above the axis, above the time axis to show a constant positive acceleration. Therefore, the velocity increases. This time we had it starting from rest. The position increases, but it increases as a parabola this time. Okay, we're going to mark numbers 3 and 4, which are more difficult, but again, we're going to use the moving man to answer these. So for number 3, a trolley pushed uphill and then rolling back. We've given it quite a large initial velocity, but there's a negative acceleration, minus 1 meter per second squared, which is going to slow the trolley down and then pull it back. Again, take a note of the vectors here, and let's see how this motion looks. And there you can see very nicely what is happening. Let's expand the time scale so we can see as much of the graph as possible. Okay, so because acceleration is negative, velocity starts at the initial velocity of 6 meters per second and then decreases. If we do the playback, we can see very nicely the different points. At the start, you've got a large initial velocity, but you've got a negative acceleration. That won't change. As he starts moving, you can see what happens. The velocity vector is getting less, acceleration vector doesn't change, and he gets slower and slower to the point where the velocity is almost stopped. Acceleration is still minus 1. When we get to this point here, this is the point where he turns around. You can see he's just turned around, so he's stationary. Velocity is naught. It's the furthest point away from the start. Notice that the acceleration has not changed all this time. And of course, because velocity is naught, we know that the gradient to that position time graph would be a horizontal straight line, also naught. Now, as he starts coming back, we see that the red velocity vector and the green acceleration vector are in the same direction. So we see that red velocity vector growing and growing as he goes faster and faster until he gets back to the end again. So that was the answer to number 3. So here we've set up the moving man to answer number 4. So we've put the man right on the right-hand side of this runway. Please imagine the runway slopes down to the left. On the left-hand side, there's some sort of spring-loaded wall so that the man or the trolley can bounce back from it. Let's first of all just observe the motion. Have a look at those vectors. Have a look at when the green and red vectors are in the same direction and when they're in opposite directions. and what effect that has on the motion. Okay, so I think you can see very nicely what is happening there. Let's go back to the beginning again, and let's just have a close look, first of all, at the position time graph. You can see beautiful upside down parabolas. The height gets lower each time because some energy is lost in deformation or noise in each collision. So those points there represent the bounces. So there was a bounce there, you can see. That's the highest point where he turns round. There's a bounce there, highest point where he turns round, and finally a bounce there. Let's look at that again with the velocity graph as well. So once again, the velocity graph is harder to understand. Starts from rest, and I think let's get rid of the acceleration vector and just look at that velocity vector. So there's no velocity vector, starts from rest. His velocity becomes increasingly negative, as you can see, until that point there, about 4.5 seconds represents a bounce. Now just watch, his velocity vector immediately changes to positive, and then it gets less and less as he's going uphill. When he gets to the highest point there, you can see velocity is 0. Position graph is at its furthest point from the bottom of the runway. And then again, his velocity starts increasing down the slope in a negative direction. With the bounce, it instantaneously changes from negative to positive, goes uphill again, reaches the highest point where you can see him turn around, and it goes down again. So I think you can see very nicely how the different parts of this graph are put together. With the acceleration time graph, it's basically -2. I'll just play it again for all of the motion, with the exception that when he actually bounces, there's a very sudden accelerating force in the opposite direction, which comes from the bounce. So otherwise, it's just the component of gravity pulling him down the slope, and then there's a very sudden force in the opposite direction with each bounce. So let's make sure that you've got all that written down. So question 3, it's easiest to start with the acceleration graph. It's a constant negative acceleration. So velocity starts at some positive initial velocity, decreases through 0, changes direction, and the position time graph is an upside down parabola. The bouncing ball, I gave you the position graph first, so we'll start from there. That's the corresponding velocity time graph. And again, sometimes it takes some time to get your head around that. And the acceleration graph is basically negative, the downhill slope, except for a spike where the velocity suddenly changes from negative to positive on the bounce. Now, we will look at some exam questions on the bouncing ball, but it might be helpful to realize that the first part of the bouncing ball graph looks like the second part of the negative acceleration graph. Can you see how those are similar? And the next part of the bouncing ball graph, showing from one bounce to the next, looks like the whole of the negative acceleration graph. So that sort of comparison might just be helpful to you. So I've mentioned to you that the bouncing ball question is a favorite with examiners. And in fact, it came up in the November 2020 exam, a graph of a bouncing ball. We'll let you try that in a moment. But in the meantime, let me do a worked example with you. This is not in your books, so just have a look on the screen. This comes from the exemplar paper in 2014. And this was question 3, the projectile motion question. Now, you'll see a position time graph, which looks very similar to the graph that you have just drawn for question 4. You can see it's the same bouncing ball graph that you see there. The difference, they've just shown the time period for which the ball is in contact with the ground. We've chosen that up is positive. They tell you a ball of mass 0.5 kilograms is projected vertically downwards. It's not just dropped, but it's thrown down at a velocity of 2 meters per second. We'll see that that will affect the velocity time graph. So here's the position time graph. Now you've got various questions about this particular graph. And it's important to understand these graphs. And the exercise that you've just done, exercise 4, will be of great help in understanding how to answer this question. Let's see how we tackle it. So 3.1, what's the maximum vertical height reached by the ball after the second bounce? Now you need to understand that bounce 1 is from time t1 to t2. Bounce 2 is from time t3 to t4. So the top of the rise after bounce to the maximum vertical height is 0.5 meters as shown on the graph. 3.2, calculate the magnitude of the time t1 indicated on the graph. I don't want to go into details here because this is equations of motion, and we will cover these thoroughly in video 6.3 on the equations for projectile motion. Basically, you know the initial velocity is 2 meters per second down. You know the value for g, you know the height, and you'll work out that the final velocity is minus 6.27 meters per second, and therefore the time taken is 0.44 seconds. 3.3, the velocity with which the ball rebounds. Well, it landed at 6.27 meters per second, but we guess the initial velocity here must be less because it didn't go as high as 1.8. In fact, it only went half as high. Again, you'll use your equations of motion, and you'll see that the initial velocity after the first bounce was 4.2 meters per second. If you're not sure how this is done, look at video 6.3 on projectile motion equations. I want to get to 3.5, which says draw a velocity time graph for the motion of the ball from the time it's projected from t equals 0 to the time when it rebounds to a height of 0.9 meters. So you can see basically the first down and the first up part of the position time graph. So first thing is we need a velocity axis, which will be the y-axis, velocity in meters per second. Don't forget your units. On the x-axis, we'll have time, as we do for all motion graph, times in second. Where do we start? We start from velocity of -2, because we're told it's projected downwards, and we've decided that upward motion is positive. So it starts from velocity of -2, and then, of course, because gravity is pulling it down, the velocity will go to a larger negative number. Then we have the bounce, where the velocity suddenly changes from negative to positive. And then, of course, from that moment, it will decrease down to 0, and 0 is the velocity at the top of that height. You can see where I'm pointing with the cursor arrow. Now, they want you to fill in these values, so let's make sure that we can. So what's the time when the ball hits the ground? Well, it's 0.44 seconds, and we know that because we've done this calculation in 3.2. What's the velocity of the ball when it hits the ground? Well, that's minus 6.27. That was also our calculation in 3.2. What's the velocity of the ball when it rebounds from the ground? Well, it's 4.2 meters per second, and we calculated that in 3.3. You'll see that usually these numbers required in the graph have been calculated in the earlier parts of the question. Otherwise, it would be too much calculation for only 3 marks. So that's what your graph should look like. Now, again, let's compare with the graphs we drew on page 13 and compare with the velocity time graph. So it's just like the velocity time graph up to that point, because this continues beyond the top of the rise. The difference is this was a ball that was dropped from velocity 0, whereas this one started with an initial velocity of -2. But you can see the basic shape is the same. Now, these graphs can be very confusing, so I encourage you to spend some time thinking about them, and we're going to give you a chance to do some exercises now. So for the first time in this video, we're going to look at some actual exam questions, and these will be found on page 14 to 16. Now, what is really important, if you're going to get anything out of this video series, is for you to try these first before you see the answers on screen. The teachers, please pause or stop the video here for 15 minutes while the students try to complete parts of the 3 questions on page 14 to 16. Now, we're only focusing on motion graphs now. We will come back to do the longer questions when we do 6.3. So on page 14, just look at the last part, question 3.4, drawing the graph. On page 15, question 3.5. And on page 16, 3.2.1 and 2. It's only 10 marks in total, but just take 15 minutes to try those graph questions. So here are the questions that are in your book on page 14 to 16. November 2018, I just want you to try drawing the VT graph, 3.4. November 2019, the questions about the position time graph. And November 2020, 3.2.1 and 2 questions on the graph. So please pause the video now for 15 minutes and just try those questions. I really hope that you have taken the time, taken 15 minutes off just to complete these exam questions for yourself. As we said, these are the questions from question 3, projectile motion, from the last 3 November exams. In 2018, we wanted you just to look at 3.4, drawing the graph. In the 2019 exam, just 3.5, 4 questions about the graph they gave you. November 2020, again, the bouncing ball graph was given to you, position, time, and 3.2.1 and 2, they're questions about this graph. But before we get to those exam questions, let's just talk a little bit about projectile motion. Now, projectile motion will perhaps be a little bit better understood if once again we turn to PHET and look at the simulation about projectile motion. This simulation is also included in the teacher pack. Now there's a cannon here which can shoot things out of it, and if we just set it off, you'll see it's going to shoot a person up into the air and back down again. Now, while you're at school, you'll only deal with vertical or one-dimensional projectile motion. In other words, objects will go straight up and straight down again. Now, of course, the cannon could fire at an angle. 45 degrees will get the greatest range. And you'll see now this is two-dimensional projectile motion, where we need to concern ourselves not just with the height and the time of flight, but also with the horizontal range. Now, you do not have to do two-dimensional projectile motion while at school, so don't worry about that. It is also possible, using the simulation, to lift the cannon up so it starts off at a higher height, just like in those exam questions. You can play around with this. Now, it's useful to have a look at the velocity vector and the acceleration vector. And I'd like you to watch these vectors as the cannon fires the object up and down. Now, it might be a little bit easier to see what happens if we slow things down a bit. And let me do that again. Now, you can see as the person is traveling upwards, the green velocity vector is pointed upwards and it's large. The yellow acceleration vector, you'll see, will not change. Because it's the acceleration of gravity, it always points down and always has exactly the same value. It doesn't change whether the object is traveling upwards or traveling downwards. If we go a bit further, you can see the green velocity vector is much shorter now. Acceleration vector still the same. At the top of the flight, the velocity vector actually becomes 0. It turns around, and now because it's in the same direction as the acceleration vector, it increases. Now, I know that matric projectile motion is one-dimensional, but sometimes it's a little bit easier to see these vectors if we shoot it at an angle. So don't worry about the horizontal vector. Let's just look at the velocity and acceleration vector. So once again, we'll fire it here. So don't worry about this horizontal vector, but you can see at this point, the velocity is still going up, although it's decreased. The acceleration is always downwards. When we get to the top of the flight, velocity is 0, acceleration still downwards. When we go a bit further, velocity is now pointing downwards and it's increasing. Acceleration is the same as it's always been, and back. So the most important thing to see is that whether we are shooting at an angle or straight up and down, there's only ever one force that acts on the projectile, and that is the force of gravity. So take some time to play with the simulation. It really is very helpful to understand projectile motion. Remember, with projectile motion, on page 13, this is example number 3. A trolley is launched uphill up a runway, rolling back from the top. So regarding the upward motion as positive, the acceleration is constant negative. That's just the acceleration of gravity, which, as you saw, always points down. It doesn't change. Velocity starts from a large upward value, gets to 0 at the top, and then gets to a large negative value. That value at the end must be exactly the same magnitude as at the beginning. And then the position time graph is simply an upside down parabola. Please note that at the highest point, the velocity is actually 0. So this is not the highest point. Highest point is when the velocity is 0. So let's look at our exam questions. We'll start off on page 14 from November 2018, question 3. The usual projectile motion question. You can read the question for yourself, and it says regard upward motion as positive. So the first question, in which direction is the net force acting on the ball while it moves upwards? And again, you should know from that simulation we've just done, the only force acting on the ball is gravity, and gravity always acts downwards. Doesn't matter whether the ball is going up or going down, gravity always acts downwards. Secondly, 3.2, calculate the time taken by the ball to reach its highest point. I'm not going to do that now. You simply take your equations of motion from your data sheet. In this case, you would say the final velocity will be naught at the highest point. So we use VI plus A delta T, remembering that A is just gravity minus 9.8, and solve for delta T. And you'll get an answer of 0.77 seconds. We will deal with these more when we do a section on solving equations. 3.3, determine whether the ball will pass point T or not. In other words, they're just asking you to calculate the maximum height reached by the ball. And yes, it will reach point T because the ball will travel up 2.87 meters, and that added to 1.6 gives you 4.47, which is more than 3.7. Now, I'm most interested in 3.4. Draw a velocity time graph. It's only 2 points, but obviously you need a vertical velocity axis, a horizontal time axis. We've learned that the graph will be decreasing from the initial velocity, which we were given is 7.5 meters per second, to 0. And we calculated there in 3.2 that the time is 0.77 seconds. Don't leave this out. The question does say indicate the following on your graph. Initial and final velocity, final is naught, and time taken to reach the highest point, 0.77 seconds. Please remember, although the velocity is naught, this is the highest point, not the lowest point. Right, let's move on. And on page 15, I'm going to go to the bottom of this one because this question is similar to the last one. This is actually from last year's exam. It was a small question, just 4 times 1 mark. So you shouldn't be spending too much time on it. But you've got a graph which describes the motion of stone A. Now, of course, that's going to be the first graph there that I've colored in blue, which goes up and comes down again. Stone B, which I've colored in yellow, is simply dropped from rest, so it just goes down. Now, you're asked various questions and you're asked to identify points on the graph. Now, please notice you're asked about 2 times and 2 heights. Now, the times I've highlighted in red have to come from the time axis. So 1 and 3 can only have answers from D, E, F, and G. You're asked to identify 2 heights for 2 and 4. And again, they can only come from the position axis. So for 2 and 4, the answers can only come from A, H, B, and C. So let's look at the answers. The time that stone A had positive velocity, well, you see stone A goes up, which is positive, and then comes down. So the only time when the velocity was positive is time D. Don't make the mistake of putting H. H is a position, not a time. Secondly, the maximum height reached by stone A, that must be on the position graph, and you can see it's simply point A, which is the highest point in the graph. Thirdly, the time when stone B was dropped. Well, we've identified that that's when graph B starts, and that corresponds to time F. And finally, the height the stones pass each other, that's the point they pass. Don't make the mistake of putting G. That is the time when they pass each other, but the height when they pass each other is point C. So that should have been fairly easy if you just understood your position time graphs for projectile motion. And finally, the November 2020 question 3. Now, like 2019, again, we have a position time graph. Again, it's not drawn to scale, but unlike the last graph, it does have actual values on it. It has actual positions in meters and actual times in seconds. And the question says, use the graph to determine these things. 3.1, define the term free fall. That's a recall question we're not going to look at now. That's just learning work for you to do. But notice that you must use the graph to answer the questions. And there's 4 questions, 2 simple ones, and then 2 that involve calculations. Let's look at the first 2. So the first one is the time the ball was in contact with the floor before the first bounce. Now the first bounce happens here. So we're looking at the time from 0.64 to 0.67 seconds. So the time the ball was in contact with the time was just 0.67 minus 0.64, which was 0.03 seconds. Very easy calculation to do as long as you understand what is happening with this graph. Secondly, the time it takes a ball to reach its maximum height after the first bounce. In other words, there's the maximum height after the first bounce. So we're looking for that time. Now one can do it with equations, but it's only for 2 marks. So the understanding will be that the ball will reach its maximum height halfway between 0.67 and 1.9. In other words, at the average of those 2 times, and the halfway time there is 1.285 seconds. Now, questions 323 and 324 are for more marks. They involve the equations of motion with projectile motion, and we will be covering these very thoroughly in video 6.3. I don't want to do them now because we are focusing on the motion graphs. So that's the end of video 2 on motion graphs. I hope it has been helpful. And apart from just being able to answer motion graphs questions, if you really understand position, velocity, and acceleration time graphs, it will help you with all other graphs, and even and especially with calculus in mathematics. Isaac Newton, you know his famous laws of motion, was also the person who discovered calculus. Please stay watching and listen to another inspiring interview. So I'm delighted to have the opportunity to speak to a friend of mine, Bheki Masikane, who works for South 32. Hello, Bheki. Can you tell us a little bit about where you're from and where you went to school?
Hello, Derek. My name is Bheki Masikane. Well, some know me as Petros. I grew up in Gwambonambi, in the far rural area in Gwambonambi, in the place of Gwamtetwa Reserve. I went to school in the local area, and my high school education was in the school called Umbia High School, which I think some of you know it.
Now, Bheki, we all remember 1994 because that's when South Africa attained democracy. What were you doing in 1994?
Wow, in 1994, that's when I was doing my matric in that same school, Umbia.
Okay. So, Bheki, this is what I was doing in 1994. I've been running these matric workshops for 26 years now. 1994 was my very first matric workshop in the university chapel. And we have this grainy photo of some of the matrics who came. Do you recognize the photo, Bheki?
Wow, Derek, I do recognize this photo. And actually, I can see some of my classmates of 1994 in this picture.
Okay, who was the photographer?
Yeah. I took this photo.
Okay.
I took this photo. Yeah, wonderful.
And Bheki, who's this young man here?
Yeah, that was myself in 1994 when I was doing matric.
So Bheki, those are some great memories for me and for you. So can I ask, 26 years later, it might be hard to remember, but were these matric workshops helpful to you?
Definitely, Derek, they're very helpful. That workshop really helped us a lot. It helped us in different ways. One, it was that we find the strategy in terms of how we should read and look at the questions during the exam, how to approach the exam answering the questions. And moreover, the workshop helped us to see the opportunities even after the matric, you know, in terms of how important the maths and science was. There was quite a lot of encouragement and motivation coming out of that workshop, even more than you can think of, just understanding mathematics and science during that time. But
Becky, that's great. If I could just
all
cut in
that
and
was
say, sorry, did you continue with
important.
your studies after school?
After school, absolutely. I studied and I was very determined that maths and science, I'm going to take that with me throughout my life. So yes, I studied at Rich Tech College, which is called Umfolozi TVET College now, in Richards Bay. After that, I did my S4, S6, S4 diploma with University of Zululand, University of South Africa, UNISA. And I've just completed my BTech degree in the UNISA on electrical engineering light current.
Fantastic, lifelong learning. Becky, what is your job now at South 32?
Derek, I'm currently doing a supervisor role. I'm a production supervisor in the reduction department in South 32. I've been working on other departments as well, but this is currently what I'm doing now. Production supervisor. I'm leading a team of about 20 people in the reduction department. That's where we manufacture the aluminium.
That's fantastic. And once again, I want to say a big thank you to South 32. They've been by far our biggest sponsor over about 30 years with Unizulu Science Centre. We couldn't have done the good work we do without their help. Becky, just in closing, it's been a tough year for Matrix 2020. Do you have a message of encouragement for them?
Remember, if you find the chance to, whatever it takes to attend and look at these workshops, and make sure that you take as much notes as possible, record or practice maths and science. You just keep on practicing, and it can take you further. So I want to encourage you and say, regardless of what is happening this year, there is no limit. You can set up and set out your own target and goals you will achieve if you fix your mind and your heart to it.
Thank you so much, Becky Masakane from South 32.